All right, so if I want to have everybody turn in their homework assignment. Okay, so short version, basically, here's the way the exams work in my class. The exam will be everything through today. I break it into technically 3 sections. Please pay attention, this is important. Break it into 3 sections. So there's a take-home portion of the exam, which is basically the first 2. I have found a job description on Cadence Design Systems website that you would be qualified for upon completion of this course. I've also posted on Blackboard a sample resume, and it will be available on Thursday. I have a 30-minute video that you can go through and actually learn how to prepare a resume, pros and cons. The sample resume is provided by Intel. They usually provide it for veteran services, and basically it's a good way of being able to describe how to actually convey your skill set. It's a big issue with coming back from military service. It's very common to have a hard time conveying their rates and their jobs into civilian capabilities. Now, where is it the issue with students? I mean, right now we have one military veteran here, but we do also have an issue with students being able to feel confident saying that their projects also count. Now, you got started new entry level position. It says you have to have 3 years of experience. You're like, how do I do that? I just graduated from college, right? Well, here's the way you do it. You basically say you worked on a project for a semester, right? So in this course, you'll be working on a project starting in about 3 weeks. The whole goal is you're actually going to build an advanced digital system using the Cadence tools. So you have 4 months of experience there. You have 4 months of experience. You've been working on C++ projects or Java projects, or you'll be working on all these other projects in your other classes throughout the rest of your academic career. Those count. If the actual specific job description says we need 3 years of experience if you're working in VLSI tools, well, if you've been working in VLSI for 3 years on your tools, that's experience. That's the best way you can do it. You've actually done the work and you have quantifiable results. So you will have the job description. It'll be posted on the PDF, which will be available on Blackboard on Thursday after class. The first thing you do, you make your new resume in the format. You tailor it to the job description the way that I have laid out there. So then, what happens is, once you do that, so let me start all over. So the way I set up the exams is you're basically preparing for a job interview, because that's ultimately what you're doing here, right? You're not here because you ultimately want to hear my great wisdom about the universe. You guys have already met Wise Bear, so you want a job. You want something that pays you and pays the bills. So the whole point of this is for you to go through process. You find this, you actually put in an application, then you prepare for the job interview. So the second portion is a set of questions where you go back through your notes, you'll ask a couple questions in the textbook as a way of preparing for the job interview. You go through, and I am actually able to quantify how much you actually studied for the exam. So how many times have you all studied for exam really, really hard and then didn't do anywhere near as well as you like? You feel very frustrated. Almost all of you, right? So I can look and say, all right, this student actually worked very hard. They did the work. I have proof, and that quantifies it. So, but in this case, you're actually going through, you're reviewing your notes, you're reviewing the material, and demonstrating a level of understanding. And then the in-class portion, which is on Tuesday, you hand in the assignment on that Tuesday, and then the in-class portion is the interview. So what you're doing is you're combining concepts in a way in which you're actually preparing for a job interview. Does that make sense? So you get to do that 3 times. You'll applied for 3 different jobs, which are available. There's Cadence, and there's one from Intel, and one from Texas Instruments. So you actually have that experience. You'll have 3 unique resumes. So every time as you're building up, you're starting to develop a habit of how you actually, try to apply for jobs. You'll have one that it'll be in a format that's been approved and preferred by Intel, which is a very prominent and successful company in your area. And then you'll have that process of being able to, you get your feet wet with the whole job application process. And what we've been finding is that this is now the third year that I've been doing this in 385 and then my subsequent classes. And then when students, they have the, how do you write a professional email, you have a really strong resume, and you have a good interview habit, students are crushing it. So ultimately this job is, what I want to do is I want to have it so that you're better, not just in my class, but you're putting yourself in a better position to get a better job and get a job that you prefer. You see what I'm saying? So I'll have that available on Thursday. So the Thursday date is what I have on the syllabus, but everything that we cover through today will be on there. So for the take home, I'll have it all in detail, but you're permitted to use the videos, your notes, and the book, the textbook, and nothing else. Does anybody have any questions about that? When you see it, it'll be clear. Just follow it straightforward. Right. Okay, so I'm sorry, I hear a lot of mumbling.
Is there a formal exam on Thursday?
Yeah, the take-home portion will be available. It'll be available on Blackboard at 11 a.m. So we will start going over the next lecture material. So everything through today's class will be on it. Yes?
And then the in-class portion will be next Tuesday?
Correct. Any other questions? All right, let's get started. So we're going to get through section 3 today, and we'll stop at the end of section 3. That'll be your assignment. And then we'll start section 4 on Thursday. But section 4 on Thursday will not be part of the exam. Oh, and the other question that I commonly get, I'll reiterate this on Thursday. The TGOs that we go over on Thursday won't be due until next Thursday because I want you doing the take-home portion of the test and studying for the exam. All right, so in last lecture, we went over the concepts of cache memory and cache hierarchy. We went over this concept of average memory access time where you have different levels of cache. And the questions I kind of commonly got were a lot of, well, how do you actually make this better? How is this done? How do you do this? So on and so forth. So TGO 3.12 here is 4 different ways to control the miss rate and hits rates on a cache. So if you increase the cache size, first you increase the cache size, more blocks can be kept in the cache, and the chances of a miss is reduced. However, a larger cache is slower. So it's more likely that it'll be in there. However, it'll be slower for it to access. Which is why your lower levels of cache have smaller amounts of memory, and then medium has a medium size, and larger cache has a larger size of memory. Also, more cache is more cache. Right? Costs more. So next is you increase the block size. So remember, the block is the smallest amount that you can transfer from different levels of cache, right? So if you increase the block size, you're more likely to swap in an element that you have, which reduces the chances of a cache miss. However, there are fewer blocks in the cache, also, ironically, increases the chances of a miss. So what this means is, let's say it's likely that it's in here. However, if you swap it out, and you're swapping it between different levels, you're actually, it's like a catch-22. It helps, but it doesn't. Does that make sense? The key thing you have to understand, if you increase the block size, more data is available if in that level, but there's a better chance it's been swapped out. So reread that part. There's more data available, which reduces the chance of a miss. However, fewer blocks in the cache increase the chance of a miss. Also, larger blocks need more time to swap. So it reduces performance. And how do you increase the hit rate? Hit rate increases with cache size. However, hit rate depends on the block size. So this TGO, there's a short version of there's no one right answer on how to design a perfect cache element. So you have to think back to those 4 design principles. Do y'all remember what those 4 design principles are? I'll give you the first one. Smaller is faster. Common case fast. Good design requires good compromise. Everyone just tired? What's that? Yes, that's correct. Okay, so this is giving you an example of when you have a large memory, and this is a cache block, you swap these in back and forth. Now, if you have a larger block, there's a better chance that the block contains the element that you have, but if you have to perform a swap, there's a better chance that the element that is in there has been swapped out to main memory. So you kind of have to find the right performance element for what it is that you want to do in your advanced digital system. Okay, and so this is where you're combining all these concepts of temporal locality and spatial locality in blocks. So if you know a general idea of how much of the size of your program, and if you're working in ASICs, which is application-specific integrated circuits, a good example of an ASIC is in a car. You have all these monitors. It's monitoring how fast cars are coming into you, so it can know when to deploy an airbag. It's monitoring your brakes. There's all kinds of different monitors in your car. And nowadays they have electronic devices where they'll actually tell you how much, how far you've driven. There's an actual accelerometer that's measuring how many times your wheel is turned, and that translates into how many miles you've gone. In short, you can, in general, predict the size of your program. So then you write your program, and the compiler puts it in memory, generally in a block. So if it allocates it using the operating system into 2 general blocks, then you have a pretty good instance of spatial locality. The issue is, let's say I have a bigger block, right? It's more likely that I'll catch these 2 that are out here. But if I have to swap it out, that means there's more likely that I'm going to actually swap out an element that I need, right? So that's what I was discussing in the previous topical guide objective. So these elements here, so basically if you're running the first few portions of your program, you put this into the local registers. The local registers will perform the operations using the arithmetic logic units. Then when you are done with them, we'll swap it back out, and then go here, get the element that you need, and swap it in, and perform the rest of the program. And so what we're going to do is we're going to start talking about how do you actually find an element in cache memory. So up to this point, we've talked about finding certain things in memory. How we swap them in, we swap them out, just like I was demonstrating in the previous picture. How do we actually do this? How do you actually find the location? So when we're talking about instruction elements, right, we had opcode, RS, RT, RD, shift amount, and functions, right? And these help in the, remember in the 5 memory mappings, that's all within the processor. So how do you actually go into the cache? So all of this 3.13 through 3.16 discuss these. And we'll go over a couple of example questions that will make these definitions make sense. So the index is the numerical value used to indicate the exact location in the cache. And so the tag, index, valid, and data fields all indicate in the 32-bit element where you're going to find everything. So the tag is a field in a table which contains the address of the information required to identify whether the associated block corresponds to the data. So what this means is that you have a certain number of bits, right? That, let's say your cache holds 32 blocks. So the tag is going to indicate the field where the block is, and the index is going to indicate which block it actually is. And so in order to actually, before you can look in there, to save you some time in determining whether or not, there's an element called the valid bit. And that's 3.15. The valid bit indicates whether or not you actually hold something. So before I, let's say I want to go check whether or not Trevor had some data, right? Well, before I go ask all these questions, like what kind of data do you have? Tell me what is the thing I'm looking for. The first question I want to ask is, do you have any data? And then Trevor goes, no. I go, okay, and then move on, right? So instead of having to search all this stuff, it improves the performance by saying that whether or not I actually have a value. So we formally define a valid bit here as a field that indicates that the associated block in the hierarchy contains valid data. And I should be that's 3.15. And so we're going to talk about two different types of cache mappings here. And then we're going to do some example problems that build up to a comparison that will be on the exam, where you're going to be comparing the difference between a direct mapped cache and a set associative cache. So a direct mapped cache is a cache structure in which each cache location is mapped to exactly one location in memory. And so we're going to be going over examples to show this, but the size of your tag is the field, is a table, a field in a table which contains the address of the information required to identify where the associated block corresponds to the requested data. That's going to be logarithm base 2 of your memory divided by the block, right? So let's say your memory is 1024, and your block is 32. So this is why knowing everything up to powers of 2 is important. So in this case, logarithm base 2 of 1024 divided by 32 is actually just the same as equal to 10 minus 5, because 10 to the 24 is 2 to the 10, 32 is 2 to the 5. So you take the logarithm of both. When you take the logarithm of two values, your division, you're dividing it. This basically comes out to a subtraction. So this value is basically just saying, figure out what the power is, and then subtract the values. And then whatever's left over, so this is the size of the index. So log base 2 of the block. So you actually have the number of elements that are, say you have telnet elements, you have, and this tells me how many times I need to swap something out. So basically, go away. What this tells me is I have 32 is the size of my block, and then I have 1024 total memory elements, which means I split them into 10 blocks, right, 5 blocks. All right, so down here I actually kind of went over a very simple example. It's like, let's use a figure below to relate the definitions to the actual memory. So I have this, I'm going to zoom out just a little here. So this is the actual block here. The main memory is the bottom here, right? So in that definition, the size of the tag is logarithm base 2 of memory divided by the block. And so what we can do is we can actually count here, 1, 2, 3, 4. And this one goes all the way out, and we have 32 elements. And then in the cache, we have 8. So what this means is, in order to swap elements back and forth, we can get these elements here into the cache, because this cache here is what I want to access. And the main memory is the slower memory that I don't really want to access as much. So what we are doing here is your index, right? The size of the index here is log base 2 of 8, which equals 3. So here's what that means. You see these elements here? I only need 3 bits to indicate which element in the cache I need, right? So if I need 101, I'm accessing this value, right? Now, if you look in main memory and how it's arranged, what you actually have here is, you see how these all end with the same thing here? 101, 101, 101, 101. So all of these, when they're swapped into memory, get swapped into that location in the cache. That's the index. The 2 bits before are the tag, which means that if I have 00101, right, I swap in this one. So now I have 00101 in there. And let's say I need 10101. The index indicates that this is the value that needs to get swapped out. And then what I do is I swap in the data, update the tag, so it's 10101, which means I'm pointing to this element, and this element gets swapped back out into that portion of memory. So that's how you use the tag and the index. So the index is, we can actually break it up into chunks, which means I have 5 different chunks, right? I'm sorry, 4. 8 times 4 is 32. And so I have chunk 1, chunk 2, chunk 3, chunk 4. Or we can say, we start from 0, 0, 0, 1, 1, 0, and 1, 1. So the reason we have the tag is that it indicates from which chunk we have it from. So this could be, example, 001. Well, it can be anyone that ends with 001, right? Well, in this case, let's say we add the tag of 10 here. That means we have this element. And let's say I add the tag of 101 here. Let's say I add the tag of 00. That means I have that one there. Does that make sense? So it's just a mapping system. So basically, what those equations in TGO 3.16 are basically saying is, I have a total of 32 bits. 32 blocks, of which 8 can fit in the cache. It can be any one of those 8. And the tag indicates, since I can split it up into 4 blocks of 8, I need to figure out which one I'm getting it from. The tag tells me which one is it from, right? Where it's associated. And then I should probably start saying, instead of saying chunks, use the term associated because direct instead of associativity. So where it's associated, and then from the index tells me what element I need to get from the cache. And so example 3.5, instead of 6.5, it's 3.5. Given a memory of 16 kilobytes, where a block is 1 byte and a cache with 256 bytes, determine the length of the index and the tag of a directly mapped cache. So this is where kind of understanding what 16 kilobytes means in industry comes into play. So 16 kilobytes means that there's 16,384 actual bytes, which is 2 to the 14. Now the number that I give on an exam problem for something like this will be no greater than 2 to the 10. So you can anticipate there'll be 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024. The size of the index is going to be log 2 of the block. So we've indicated a block is 1 byte and that we have a cache of 256 bytes, right? So log 2 is 256. Which is going to be, is equivalent to, and 256 is 2 to the 8. So that just means it's 8. So what's going on here is we now know that we have a memory that's 2 to the 14 and a cache of 256. That's 2 to the 8, right? So now we know that our tag is just log base 2 of 2 to the 14 over 2 to the 8, which is really the same as 14 minus 8, which is going to be equal to 6. So I have 6 chunks, in quotes, or elements that I can associate, and then I have 8 of those. And then last, certainly not least, this byte here is 8. That means that the memory is 8 bits. So I am allowed to indicate, I have a tag that indicates where in memory it is. I have an index, which tells me when I put it in the cache where it needs to go. And then I'm actually storing 8 bits of value. So that's example 3.5. Does anybody have any questions about this? Yes?
How do you know that 8 bits for memory?
Because they indicate where a block is 1 byte. Here. Given a memory of 16 kilobytes where a block is 1 byte and a cache of 256 bytes. So this value here goes there. So basically this is indicating, this is an actual value in cache. It's basically saying where I came from, where you need to go to find me, and what I actually contain. So think of it this way. So a tag, we have 1, 2, 3, 4, we have 10 rows, right? So the tag tells me that if I have 10 rows, so that's 10. And then if I had 1, 2, 3, 4, 5, 6, 7, so it'd be 10 to the 7 is our total memory. That's how many, we can hold 10 times 7. So we can hold 70 people in this group, just in shares. So in order, the tag tells me where did I initially get my row, right? So if the program tells me I get Victoria, I go to row 7. 1, 2, 3, 4, 5, 6, 7. And then her index is 1 because she's in the first share. So if I just, so now I bring Victoria back to Mercury. Victoria performs the operation she needs to do. Now, if I need to perform a different operation, I need Darren, right? Darren is also in the first first index. So if I need to bring Darren into cache, I'd have to swap Victoria out and then bring Darren in. Does that make sense? That correlate how tag and index works. And then each of you contain a byte of information. So Victoria would come in, she would provide that byte of information to do some sort of operation. We put Victoria back in the main memory, then bring Darren in. He has his byte of information, which is the 8 bits here. So now this is example 3.6. So we're now given, so this, you don't have to draw this out like this. It is this last bit here. That's the right, the last part is the right answer. So you don't have to draw all those out. What I've done here is to show you what the cache looks like at every single step and what's actually going on. So this is kind of a type of question you'll see on the exam. So given a direct mapped cache with 8 words and the address references 22, 26, 22, 26, 16, 3, 16, and 18, show the sequence for accessing the cache. Assume the cache is initialized as empty. So when I assume the cache is initialized as empty, what that means is all the valid bits are no. And it registers as a cache miss. So what ends up happening is, the first step is, go through, find the numbers, and convert them to 5-bit binary. So 22 is 10110, 26 is 11010, 16 is 10000, 3 is 00011, and 18 is 10010. And so we have 8 words. This is the important part. 8 means that my index is going to be 8. So I have an index of 8 words. That means which means my index are these 3 values, and my tag is these 2 values. Does that make sense? So that way, whenever I swap out, I have to find the value that's here, swap that out, and then update the tag. So first we initialize it as empty, and then the next step is I'm putting in 22 first. So 22 has an index of 110. So I update the tag as 10 here, update this value as yes, and then data is just memory with that value that's in there. Now it's a word, so it's 32 bits. But often in the exam, people will put M10110, and that's a fine full credit answer. Step 2. Now we're going to put in 26. 26 is 11010, so its index is 010. So we put it there. We update this value as yes, and we update the tag as 11. So that's also a miss, right? So next we do, the next value here is 22 again. So 22, we look there, we look where it's supposed to be. The valid bit is yes, the tag is 10, which means this is a cache hit. We found what we need, so we indicate step 3 is a hit. Step 4 is 26 again. 26 is there. First we look at the index, it's 010. We then look at the tag, it's 11. That means it is in fact 26. It's the value we want. Therefore, we have another cache hit. So the next value is 16. 16 is 10000. So we go to an index of 000. It's not, so we update it to yes. We update the tag to 10, and then we update the memory to that element. Then step 7, 8, 9, we have 3. So 3 is 00011. So that means our index is 011. We look here. It's a no. So we update to yes. We update the tag to 0, and then we update that memory element. Next is 16, so it's a cache hit. It's there. And then the last value of 18. 18 is 10010, right? Well, we already have a value in there of 18. So we already had 26 in there. So if you look this value up here earlier, see how we had 010, we have 26, we have 11. So putting in 18, it's 10010. So what happens is we look at this index. We do have something in there. I check the tag. It's not the tag I expect, which means I have to swap the value out. So that's a cache miss, and then I put that value back in. So this is the correct answer here. That's the final step. So what a lot of students will do is they'll scribble a little thing on the side, and they'll just say 22. This will be a shorter version of a correct answer. So they'll write these values out, and then they'll have worked through it enough where they understand tag and index, so they know. So it's going to be tag 22, so it's going to be 110, right? And then they'll have 26, so they'll have 0, 1011. So that's a miss, and then hit 22, hit 26. Then they'll go 3, so that's 00011, miss 0, and then 16 is 10000, and then they'll look at 18 and they'll say 10010. So then they'll go, wait, so I just swapped that out, and then you write those values into the table. This is how students will commonly end up doing on an exam instead of having to write all these out. Yes?
But we just need that final table.
Yeah, all you need is the final table. you need the final table, and you need to indicate the hits and misses. Is that clear? Okay. And so while that's going there, I'm going to kind of talk about what a set associative cache is. So a direct map cache means that I have I have all of these. Each tag indicates where it is in the element, and that each element in the cache relates to the element in memory, right? And it does so with it's related by the index. So a set associative improves the probability of a cache hit. We do so by, instead of having 8, we have 2 blocks of 4. And that's what we'll cover in this course, is a two-way set associative cache. So you're going to think of direct associative as a one-way set associative cache, and then set associative of 2 is two-way set associative. So it means we're just splitting up into 4. And if we go over an example, you'll see that doing the same elements actually shows different levels. I mean, it's able to retain more in memory. So formally defined set associative cache is a cache structure that has a fixed number of locations which each block can be placed. And in example 5.7, I'll go over an example of a two-way set associative cache. Okay, so we have the same number of inputs, right? Okay, I'll go back later. Given a two-way set associative cache with 8 words and the address references of 22, 26, 22, 26, 16, 3, 16, and 18, show the sequence for accessing the cache. Assume the cache is initialized as empty. So it's the same thing as before. We write out all the values. And so we initialize the cache. So what ends up happening is you have an index, you have the tag, but you have 2 data elements instead of 1. You see how it still has 8 here, it still has 8 here, and it relates the same way. But what ends up happening is the index has the 2 bits, and then the tag is going to become 3. And the reason that is because, and we'll work through the example here in a moment, but it allows you to actually store more elements. So first what's going on here is 22 is 101 and then 10, right? So first we go to 10, and so these are all the steps right here. So we can work through, and that's the final answer. So, but we'll go through, so what that's blocked off, that's what you can write on the TGO and get full credit. So we start here. We go to 10. The elements know, we mark it as yes. We put 101 here initially, right? And then memory element of 10110, right? So 26 is 11010, right? Now, if you recall from the previous question, if you had a matching index, you had to swap out, right? But in a two-way set associative, and this is where the benefit comes in, you just plug it into the second associativity. And the benefit of this approach is that you can check twice before officially having a cache miss. So it increases the probability that you can store an element, and ultimately, because you reduce the probability of a cache miss, you improve the average memory access time of your memory system. So this is why we designed it this way. So in this case, we would update this to yes. We put 101. I'm sorry, we put 110 here, and then memory 11010. Does that make sense so far? The next step is 22 and 26. They're both hits because they're already there. Now 16 is the next step. It's a miss. The index is 00, and the tag becomes 100, like so. So we put this value in here, and it's fine. 3 is also a miss. 3 is 0, 0, 1, 1. So it goes into 1, 1 for the index and puts 0, 0 here. Now in this case, 18, 1, 0, 0, 1, 0. So that's where you have it there, right? So then what you have to do is the first one's filled, the second one's filled. Well, now I have to swap out one of them. So without going into too much detail into into operating systems, in this case, what LRU stands for is least recently used. So whichever one you use, you put in least recently is the one that gets swapped out. In this case, we have 22, 26, 22, 26. So 26 is our most recently used, and 22 is our least recently used. So 22 gets swapped out, which is why we have 1, 0, 0, 1, 1. I'm sorry, 1, 0, 1. Take 3. 1, 0, 0, 1, 0 there. Does that make sense? Yes, Kate.
So would that not be a hit?
It's a miss.
But
Miss and overwrite.
I'm confused because
A cache hit is if the element that you're looking for is there, right? So 18 goes there, right? Is 18 in the cache?
no,
22 and 26 are. So that means that if it has to be a hit, so the reason why 22 and 26 are hits is because 22 and 26 are in the cache. Does that make sense? So here I have 18. I'm looking for 18. I know that 18 ends with 1, 0, so I go to my tag. There's 22 and 26 in there, not 18. So that means it's a cache miss. Well, we're going to go over one more example of this, and that should all make it very clear. Sometimes it's just repetitions. Any other questions? I know this can be kind of a confusing concept. Okay, so the last example in this section is where we just combine them together. Now this will be bigger than what you'll actually experience on the exam, but your exam question on this topic will be along the same area. Basically, I won't have this many numbers. The whole point of having this many numbers on the example problem is for you to work through it and work through an example. Does that make sense? So the purpose of this problem is to compare direct associativity and set associativity. By doing this problem, you can demonstrate that you understand how cache access works. You can demonstrate that you understand what a tag and an index and a block are. And you also can demonstrate that you can correlate the address, the cache, to how you actually find the information. So Kate, on that front, what you were just asking about, how you can demonstrate when you know something's a cache hit versus a cache miss. So this is example 3.8. Given a cache hierarchy with 8 words. So it's going to have 8 words. So if it's the direct associative, it's going to be just one block of 8. Set associative is going to be 2 blocks of 4. The direct associative is kind of an index of 3 bytes because, I'm sorry, 3 bits, my apologies, 3 bits because 2 to 3 is 8. When it's two-way set associative, it takes those 3, splits it in half. So now it's just 2 blocks, sorry, 2 chunks of 4. So therefore, you can have your index. The key thing is you have your index of 2, and you have 2 actual elements per index. So you have the following set of memory accesses. And so we're combining concepts. We have a cache access time of 5 nanoseconds and a memory access time of 20 nanoseconds, which means that cache hit, 5 nanoseconds, memory access time, miss is 20. And so we have the following set of memory accesses: 22, 28, 31, 22, 16, 13, 31, 8, 5, 13, 8, and 5. So A, if the cache is a directly mapped cache, show the sequence for accessing the cache and calculate the total time. And then for part B, if the cache is a two-way associative cache, show show the sequence for accessing the cache and calculate the total time. Then calculate the improvement in performance over the directly mapped cache in part A. So now we're starting to combine concepts. You have computing performance from section 1. Now you got some memory elements from section 3. Now we're talking about some average memory access time here. So it's your solution. First, you want to go through all the unique numbers and convert them to binary. So you have 22, 28, 31, 16, 13, 8, and 5. 22 is 10110. 28 is 11100. 31 is all ones, 11111. 16 is 1 and then 4 zeros, is 2 to the 4. 13 is 01101. 8 is 01000. And 5 is 00101. So that means in a directly mapped cache, and so students I've seen in the past they'll write these out, and they'll actually have a directly mapped cache that this is your index. They'll start lining them up like this. And so for those of you who like to try to think like the instructor, and you start seeing like, okay, well, 13, 5, and where's the other one? Yeah, 13 and 5 are the same. You have 110, right? So that means 13 and 5 are going to be involved somehow. 8 and 16 are going to be involved somehow. So it's going to be, so you can know, you see like the 8, 5, 13, 8, and 5. That's when you know already, you can start to see that this is how I put the question together. So you have a lot of cache hits and misses in here. So this is an example of a fully correct answer for, so you have 22 and 28 are going to be a miss because that's the first time anything goes in there. So 22 is 110, so you put it into 110. You update the tag to 10. 28, the index is 100, so you put that in there. You update the tag to 11. Next is 31, so that just matches these values here. So 31 is all ones, right? So it's a miss. You have 111, so you update the tag. You update the index, and then the tag is also 11, so you update that value. So next is going to be 22. 22 is a hit because we already have it in there. We look at the value of 10. We look at the tag. It's there. 16 is a miss because we look at 000. There's nothing there. Then we update it to 10000. So now 16 is in there. 13 is also a miss because we look at 101 and there's nothing there. We update the tag to 01 in the memory. So 31 is a hit. So look at that. We look at 111. We see that we have the valid bit is so. Then we look at the tag. It is 11, so we have a hit. So next we get an 8. Now 8 is 01000. And so Kate, to kind of elaborate on your question from earlier. So in this case, where we hit here, where it says 8 miss, overwrite 16, what that means is the current tag is 10 and the index is 000. And it contains the value of 16. 8 has the same index, but has a different tag. So it's a different element in memory. So the way it works is it asks, do you have a valid bit? Yes, I contain an element. What is that value? I have 16. I'm looking for 8. Okay, well now I got to go get 8, right? So it goes, gets 8, puts 16 back, brings 8 in. So does that clarify your question? Okay, good. So now it's updated. So instead of 10, it's now 01. And same thing with 5. 5 is 00101. 13 is going to be 01101. So they have the same index. So the same thing goes to the value there. Do you have a value? Yes. Are you 8? No, I am 13. Okay, now it swaps them out. So 5 overwrite 13. And then 13, okay, I just put them right back there. 13 and 5. And then 8, I have a hit, and then 5, overwrite 13. So you're going to start seeing that pattern. Now, before we get to set associative, why do you think, I want you to think about this way, what I'm trying to demonstrate. It's not just putting random numbers there. There is a method to the madness. You see how I'm getting this 13 and 5, 5 and 13, 5 and 13 multiple times, right? So think about set associativity. Think about the benefit. If I can hold 2 elements in a tag instead of 1, that means I don't get that going back and forth. I don't get that thrashing. So the way I'm going to set up the problem is I'm going to have a direct map cache where there's going to be a number of swaps, and then you can see it when we get down here to the access time. And then there's going to be a set associativity where implementing set associativity solves that swapping. And you'll see it pretty quickly when you light up the problem. So in this case, the best way to go through it, you just go 1, 2, 3, 4, 5, 6, 7, 8, 9 misses, and 3 hits. You go back to the problem. You saw for each hit, it's 5 nanoseconds, so it's 3 times 5, plus 9 times 20. So that comes out to 195. See that? So that's the access time of that particular program. So before I go to set associativity, does anybody have any questions on what I did for direct there? Yes, I'll go to Alexis first, then Kate.
I was just going to ask why when you take 8, it's still no.
Oh no, it's a hit here. 8's initially a miss because there's no value in there, and then when you get to 8 here, it's a hit.
The valid tag.
That's the value. If anything's valued in there, it should be yes.
Yeah. Okay. Where is it? 1-0. Oh, 1-0-0. The very first one.
Oh, it should see yes. Okay. Does that answer your question? Okay. Yeah, that professor screwed up. Kate, do you have a question? Okay. Does anybody have any other questions or catch any other of my mistakes? Okay, so in this case, now we're going to set up a set associativity for part B. So in this case, it's all empty blank. Here's though I got it right this time in terms of yes, except you should also say yes here. So the sequence, 22 is a miss because it's empty. 28 is a miss. 31 is a miss. So we update, in this case, 22. It's going to be 10. And the tag's going to be 101, right? Like before. 28 is going to be 11100. So that's going to go into the index, and then you update the tag. So 31 is a miss. It's all ones. Goes into 11, right? And then we update the tag, and you can see here any value that's empty should not empty should say yes. So yes, yes, and then anything that's empty should say no. So then 22 is a hit because it's already there. 16 is a miss. Now 16 is going to be 100. So we put it in the tag there, right? So it's there. And then what ends up happening is, so 13, we come in and it's 01101. It's a miss. It's not there. So we just put it in the second element for 01, right? So now instead of having to swap them out, it's put in. So 31's a hit because it's there. Now 8 is a miss. So we have to overwrite 28. So the reason why you have to overwrite 28 is because 28 is 11100. We already have 16 in there, 10000, right? So it has to go to the least recently used, which is 28 because that was the one we have to use before, and then we overwrite that value. Then 5 is a miss. Now you see here, we only have one overwrite, but we're going to start getting hit, because now we put the value of 5 in there, so we get 0, 0, 1, 0, 1. And so 13's a hit, it's in there. Then 8's a hit because that's in there as well. And then 5 is a hit again. And so you compare it, we have 7 misses and 5 hits. And so if this was a program that went on for hundreds or thousands or millions of instructions, we'd end up just using the same cache values over and over again, which is where when you get to your average memory access time, that's where you get your 95%. So when you have these values, you get a lot of initial misses, but then as they start building up. So here, we just have 5 times 5, which is 25, 7 times 20, which is 140, so that becomes 165. So then your improvement in performance is just 195 over 165. And I put in the ratio number, but you don't have to because I'm not grading how you put stuff into a calculator. Does that make sense? Any questions other than I didn't update the valid bits correctly? So the rule of thumb, it's simple. If there's something in it, the valid bit is yes. Otherwise, no.
Yeah, why is the index two numbers on the set associative of 3 on the direct associative?
Okay, so direct associative means that it's just all one block, right? So then what happens is set associative, I split them in half. So what it means is the index just tells me where I can, it's like a house, right? So it says direct associative, I have 8 houses, but I can only store 1 element. In set associativity, I have, instead of having 8 houses, I have 4 houses, but I can store 2 in each. So that means, and this is an example, and the one that you'll do on the exam will also be an example of showing that if you do set associativity, it will improve your hit rate. Okay, did that answer your question?
Yeah.
Awesome. Any other questions? All right, so on that note, hold on, let me get out a notepad. Okay, what's going to be on the exam? D's like, boom, this on your face. What's going to be on the exam? Oh, I'm sorry, what did you say? I thought you said an actual answer. Yep. So remember, define and differentiate between computer architecture and computer organization. And I should always say, do my little caveat, the exam will be some subset of these topics. Meaning that the way I do it is I will set up the exam. I'll answer the question you asked me. Well, so what I mean is I will write up the exam. I take the exam. I multiply the amount of time it takes me to do it by 3. And if the exam takes more than 75 minutes, I cut a couple of problems. Does that make sense? So I've been doing this for years. You guys are just learning, so I give you 3 times as much time as I take. It's not like in calculus where they come in like, well, this only took me 10 minutes. Like, yeah, well, you've been doing this your whole life. Thanks for the condescending comment. No, I believe that what I found is that's a fair ratio in expertise. So I take it, multiply it by 3. If I find it's a little long, I cut a problem. So that means it's some subset, and whatever we come up with here, I will not ask questions outside of that. Okay, what else? Philosophy of MIPS. No, it's like the question from the quiz. So review the quiz answer key. What else? Amdahl's law. What else can you expect? Yep, some sort of performance question. What else can you expect? So start getting to section 2. Look for those key things to remember me drawing up those stars.
All under performance.
Yeah, it's all that. So basically, that's that question that I have on the quiz is an example of a comprehensive. It asks all the types of questions, demonstrates that you understand performance comparison, you understand average CPU time, and how the number of instructions correlate to the actual runtime of a program. And then you correlate it to clock rate, which is in that problem I think 3 gigahertz and 2 gigahertz, and so that's a performance question.
Is this the part that's gonna be on Tuesday?
Yes.
Full ladder.
Yeah, you'll have to do some sort of design with a full ladder. Let's see. You'll need the full ladder to compare. So know the. Let's see. Let me bring up section 2. Okay, so you need to do some sort of question involving. So here's your arithmetic, so we can go over these. I don't think I'll have the time to ask to be able to define an adder. But what else do you remember from this? Yep. IEEE 754, very good. So you have to do some sort of IEEE 754 floating point addition. And then sign multiplication. And then what are the two types of division? Restoring and non-restoring. Okay. So what was the key thing to remember when you do the multiplication? Only write when it changes in the table. Don't rewrite everything. That'll save you some time. When I do the IEEE 754 floating point addition, you will not be required to convert a value past 4 binary digits. Remember 0.5, 0.25, 0.125, 0.0625. You won't be required to do anything past that. So that will be your stuff from section 2. So it'll be some question like that. Calculate the sum. Example 2.3 is an example of floating point, then signed and restoring and non-restoring. So from section 3, what do you think is going to be on there from section 3? That's the 3.3. That's the 5 different types of memory addressing. Yep. Yes, you review the question. Define, state, define. So in this case, and then draw. So state is you have to state it's an immediate. You have to then define it as the operand is a constant within the instruction, and then you have to draw it opcode, register S, register T, immediate value. Then you have to draw all 5 of these. And this demonstrates that you know that you get the value from the register. That's 5 bits. You have a 5 to 32 decoder. That 32 bit value tells me which register I get. Does that make sense? So if a register, the operand is a register, and it shows me how to get the register value. And then you'll be asked for all 5. And then, what else? There's 2 other main definitions that I want you to know from. Yep, for what's the equation? Yeah, so that's the average memory access time. Very good, D. So you derive the equation by solving the problem. And then there's one other one in between there.
Locality.
Yep. So define locality. That would be TGO. 3.4. And then there's one more. Yeah, you want to do the compare, direct, and also, this will be on the video, so you don't need to do the sneaky thing where you do the pictures. Just for the future, I won't snap on you. Other professors in our department, you can do things like that, especially if there's, what's the word I'm looking for? Intellectual property, it's copyrighted. Sometimes they might snap on you, so we'll just use this as a, this is fine, it is what it is. It's also available on the video, so.
I can hear you any word problem. Like
Yeah, you'll just that's the last problem. Example 3.8, I believe it is. The last example from the. Yeah, this. Yeah, 3.8. Your in-class portion of the exam will be some subset of these problems. So basically, what you can go through is you can just find the problems that we did in class, create your own practice tests, change a couple problems if you want here and there. So this is, you can study for that. And so the take-home portion, there'll be, you'll see these problems plus a couple other things that'll help you practice. And I'll go over the exact details on Thursday. So those of you who were late, please come up and see me. Other than that, you are dismissed. And like I said, you all knew what was going to come on the exam, right? So.